sections are 5.1 and 5.2. I kind of just mix those together and deal with systems of equations. And no matter what size system of equations you have, every single system, every system of equations has 3 possible outcomes. The first one is the most common one that we see in a math class. It's that there's one solution. One exact solution that fits all 3 or both of the equations. If it's two equation system, it's 3 equation system. One solution that fits all 3 of those. If it's a 20 equation system, which we won't do any that big, but if we were doing that, that's still a possibility. One solution is the most common that we'll see in math class, and it's the one you want to happen because you want to be able to find an answer if you're dealing with a system of equations anyway. So one solution is a possibility, and then no solution is also a possibility. Okay, there is not an answer that works for all of the equations in that system. Okay, and then the third option is that there are infinitely many solutions. That there's more than one way to do it, and that is not quite as popular a choice because it is dependent upon whatever one variable is changes what the value of the others are, and it creates just an infinite number of solutions. The math words that go with these situations, and we'll just touch base on these. These are the words you'll hear me say the most, is what we've already got written here. But there are words that go with this. Consistent means there is an answer. So if we say consistent, that means there's an answer. So one solution or infinitely many solutions are consistent systems. And if it's only got one solution, it's independent. Independent systems can go different directions, right? If you're independent, you can go a different direction than everybody else in this room. You just happen to be in this class all together, right? If you're consistent and dependent, consistent and dependent is infinitely many solutions. We're going to use the word one solution, no solution, or infinitely many solutions most of the time we're talking about this. But these are the mathy kind of words that you might see with that. No solution. If consistent means there is an answer, what's the opposite of consistent? Inconsistent would be the most simple way to say that. And a no solution system is inconsistent. That's the mathy word that goes along with that. So be able to relate those together, but we're going to say one solution, no solution, or infinitely many a lot of times in here. So able to recognize those. Now we'll start off with linear systems. Linear systems have lines, and particularly straight lines, not curves. We'll get into that next week. We'll talk about systems with equations that are polynomials and they curve, or maybe they're rational equations and they've got asymptotes and different pieces and things out of that. So we'll get with nonlinear systems next week. But we're going to start with linear systems here. And in 2D, which just a regular linear system, you know, y equals mx plus b, that kind of equation. If there's one solution, it looks a lot like this. That one solution is the place where those two lines cross, and it's an ordered pair. one solution. The lines cross one single spot. Okay. Got a coordinate plane. And if there's no solution, what should the lines do? Not cross. If lines don't cross, what are they called? Parallel. The lines that do not cross. So there's one line, another line. They're parallel to one another. They never cross. So that's no solution. Parallel lines, if you think about the equations of the lines, the slopes are the exact same if they're parallel. So that's what makes them parallels. The slopes are the same and the y-intercepts are different. If you're looking at the only other option would be an infinitely many solutions situation. And infinitely many solutions, you may have two equations. The graphs lie right on top of one another. And this is a little tougher to draw than you would think it would be. I'm trying to be off of them by just a little bit so you can see that there's a red one and a blue one. They're laying right on top of each other is what I'm trying to show there. The two lines that lie right on top of one another have infinitely many solutions. Infinitely many solutions in a linear sense. Both lines have the exact same slope, same y-intercept, same x-intercept, same everything. They're lying right on top of one another, so they're touching each other in an infinite number of places. If they don't touch each other at all, there's no solution. They have to be parallel for that to be the case. If they're not parallel, then they have to cross at some point, and that's when there's one solution. So we're going to look up at how we can solve the systems of equations with these three scenarios happening. So let's start with a system. 2x minus y equals 2, and y equals negative x minus 2. Okay. A couple different ways to solve this. The first method that I want to talk about is substitution. Substitution says you're going to take something and substitute it into one of the equations. When we look at an equation system like this, we see that this equation has y equals some stuff. You may have an equation that has x equals some stuff, but it tells you that y is equal to negative x minus 2. So what that allows you to do is take this stuff and replace or substitute that in the place of y in the other equation. Okay? Substitution means you replace something. So when I replace that, we'll have 2x minus parentheses negative x minus 2 is equal to 2. So what I've done is taken that first equation, instead of putting y in there, I put what y was equal to in the place of it. And then I need to simplify that and get x by itself. And that's going to help me find out what x is for this system, if there is an x. So I would distribute this negative 1 that's there. All right, so that'd be 2x plus x plus 2 is equal to 2. And then 2x plus x would be 3x, right? We have 3x plus 2 is equal to 2. And then let's get x by itself, so we're going to subtract 2 from both sides. 3x is equal to 0. What times 3 would give me 0? 0. So x has got to be 0. So we have found a solution for x. It's 0. How can we find a solution for y? Put in 0 as x in either of the original problems. It doesn't matter which one. I'm going to go to the second one because it says y equals some stuff with x. So I'm going to take this and plug it in to the equation. Well, that's negative 1 times 0 minus 2. Well, that cancels out. And it's just negative 2. So we get this as the y value. So this means this has one solution. that final answer is an ordered pair, 0, -2. Okay, I put a star by that because that's your final answer. Yeah, on your Canvas quiz and stuff, it may only ask you for X on a system. But so if it did only ask for X, and you found X first, then you're done. But sometimes it's going to ask for the whole ordered pair solution to that. So be prepared for that. But using substitution is definitely a great method for that, for particular system. But you can find an ordered pair. So there's one with one solution. We see what it looks like there. Again, that's going to be the most common occurrence is one solution. We're going to see that quite a bit tonight. Let's look at another system. 3x plus 2y is equal to 11. Negative x plus y is equal to 3. Again, we're going to try to use substitution here. I know some of you may remember using other methods for solving systems of equations from maybe your high school math class, or maybe you remember from doing all the extra studying and stuff that you might be doing. But either way, we're going to try to use substitution here to solve this one. And what you look for if you're going to try to use substitution, which is a good method for solving systems, is you look for the easiest one to get a variable by itself in. So when I look at the first one, I see a number in front of each of the letters. That usually means that's not the easiest one to work with. Sometimes it may be the only one to work with. But this one, if I try to get x or y by itself, I'd end up with some fractions in there. We kind of want to avoid that if we can, right? But when I look at the second one, I see ones in front of both of those. So that means this is going to be pretty easy to get one of those letters by itself. I think this would be easiest to get y by itself. And that's what we're most used to doing, is getting y by itself. So how do we move this x over to the other side?
Add it.
You add it because it's a negative. And if you do that, we get y is equal to x plus 3. And we can take that stuff and replace y in the first equation. So we're getting one of the variables by itself, and then taking that stuff and substituting it into the other equation. Don't get in a hurry and substitute it back into itself, because that'll just get you nothing. It'll cancel everything out and it won't work. So go back to the other equation and work that out. So we got 3x plus 2 parentheses x plus 3 is equal to 11. And we need to get x by itself. So we just need to start working our way to get x together. So we got 3x plus 2x plus 6 is equal to 11. Like terms there, we got 5x plus 6 is equal to 11. And then subtract 6. 5x is equal to 5. Oh, that's nice. X has got to be 1. So we get a solution for x, and we take that and find y. And you take this 1 for x and you plug it into any of these original equations, or even this one here where we got y by itself. It doesn't matter. Pick whatever you think's easiest. I'm going to go right here because I think that's easiest. Because I can do 1 plus 3 pretty quick, right? Y equals 1 plus 3. Y is 4. The ordered pair, 1, 4. That right there is what you want for your final answer, is an ordered pair when you look for the higher answer for a system. Ordered pair. So substitution is a valid method for solving systems of equations. Is it the only way? Absolutely not. Systems of equations can also be solved using graphing, where if you get the slope-intercept form of the equation and graph it and see where they cross, it works. Graphing's probably not the best way, which is why I don't even go over it, because if they don't cross at a nice point, it's hard to estimate. I can't eyeball the difference in 1.4 and 1.5, where algebraically with the substitution, or the next method we're going to talk about is called elimination, I can get an exact answer because I'm solving an equation, getting x or y by itself. That's doable. So let's look at the next method, which is elimination. And I like this method better. It's important to be able to do both, but I like elimination a lot. So we're trying to cancel out a variable. In order to cancel out variables, we need opposites on the variables in the system. So let's look at our system. Let's say we got 3x minus 4y is equal to 1, and negative 3x plus 6y is equal to 7. All right, so when you're looking at a system of equations, and maybe they don't even tell you which way to solve it, maybe they say solve this system of equations. If it gives you the option, you want to look and see, okay, is this a good one for substitution? Is this a good one for elimination? Or maybe neither of those. Maybe there's another way I want to do that. And for this one, I look at it and I see I don't have a plain variable. So that, to me, automatically says, I ain't doing substitution because I can't get y or x by itself real quick and easy. So I look at elimination. And this one is a great candidate for elimination because look at the x's. Got a positive 3 and a negative 3. Those are opposites of one another. Anytime you have opposites on the same letter, it makes eliminating that letter super easy, right? So if we took these two equations and just added them together, like just a big old addition problem. Notice how all the y terms are lined up. That's what you need to have happening. You need to have x and y on the same side and the numbers on the other side of the equal sign. You need to have that in order to do elimination. And if I add positive 3x plus negative 3x, they cancel each other out or they eliminate one another. That's what we want to happen. And then on the y's, I say negative 4y plus positive 6y is 2y. And then 1 plus 7 on the other side of the equal sign is 8. And now we've got an easy one-stepper to get y by itself. Divide by 2 and you got y. Bless you. Okay, so we got y equals 4. Now, that's super easy to get the first variable. It's a little bit more difficult to get the second variable because you don't have something to just plug straight into and work out. You've got to do some more equation stuff. But we got y is equal to 4. So I just pick my poison. I pick whichever one of the equations I think is easiest to work with to plug that into. I'm going to plug it into the first one. 3x minus 4. And instead of y, I'm going to put 4 because that's what y was equal to, right? Taking this 4 and substituting it back in. So substitution is still part of this, but you use elimination to get your first answer. And so that gets us 3x minus 16 is equal to 1. And then get x by itself. So I'm going to add 16. 3x is equal to 17. And then the last step would be divide by 3. And we get a fraction, 17 over 3. And that's okay to get a fraction. That's what this one is. Works out to be the correct ordered pair, 17 over 3, comma 4. How can I tell if that's correct? I can take this ordered pair, x and y, and plug it into both of these equations and make sure it's correct. If I take 17 over 3 times 3, that's 17, minus 4 times 1. 4 times 4. 4 times 4 is 16. What's 17 minus 16? 1. So it works in the first one. If I take it into the second one, this would be negative 17 plus 24, which is 7. So it works in both equations. To be the correct answer for a system of equations, then it's got to work in both equations or all of the equations in the system. We may have we'll get some that are larger than this later on. Let's do another elimination problem. One that isn't quite as easy, but it's still not hard. change up that second equation. So 3x minus 4y is equal to 1. Then 2x plus 3y is equal to 12 is our system. And when I look at this one, I see no opposites in there. I don't have a positive 3 and a negative 3 like I did on the previous one. But I can make that happen. Okay, so what I've got to look at is to look at those numbers in front of the variables and try to see, could I turn them into the same number using multiplication? Okay? And here's where you just got to make a choice. Do I want to eliminate x or do I want to eliminate y? It doesn't matter which one. On this one, my eye is drawn to the y's because they already have the positive and the negative sign. And anytime I don't have to change the sign on something, that's going to be one less thing I can screw up. Right? Because anytime you introduce a negative into a problem, it always makes it harder, right? What number do 4 and 3 both go into even? 12. So we just need to turn those into 12s. And that will help us eliminate. So what times 4 will give me 12? 3. So I'm going to multiply this first equation by 3. The whole equation by 3. That's going to give me 9x minus 12y is equal to 3. So I'm taking that whole first equation and multiplying the entire thing by 3. On the second equation, I need to multiply by 4 to turn that 3y into a positive 12y because I want opposites there. And that's going to give me 8x plus 12y is equal to 48. Now I can do that elimination step where I just add the two equations together. The y's cancel out. They're eliminating one another. That's what we're trying to do. And then 9x plus 8x is 17x. 48 and 3 is 51. So we got a one-stepper there to get x. Do your division. 51 divided by 17 is 3. And now we got to find y that goes with that. I always go back to an original equation, especially when I've had to multiply both of them, just because it gets the numbers smaller again. I always try to work with smaller numbers if possible. So I'm going to go take that 3 for x and plug it into one of those equations. I'm going to go to the second one here because it's all positives. And I don't have to deal with a negative sign messing things up for me. So I'm going to take 3 and I'm going to plug it in for x in the second equation. So that's going to be 2 times 3 plus 3y equals 12. So I'm taking this 3 that's right here that x was and replacing x with it in that equation and working that out. So that's 2 times 3 is 6 plus 3y is 12. Next step would just be subtracting that 6. And there's 3y is equal to 6 divided by 3. Y is equal to 2. So we get this ordered pair, 3, 2. That's our final answer for that problem. Final answer is going to be an ordered pair there. Using elimination to cancel out. Questions about that method? We're going to do another one like that. Just looking for, making sure we're getting the idea here. Let's say we had 8x minus 2y is equal to negative 4, and negative 4x plus y is equal to 2. This is one of those that you got options on. You could use either substitution or elimination to solve it. You get the same answer no matter which method you use. Okay. So instructions on the canvas or on the test may tell you to use substitution. They may tell you to use elimination. But if it just says solve it, and even if it says to use elimination, but you like substitution better, nobody will ever know you didn't use substitution to solve that. Or if you like elimination better, nobody will ever know that you didn't use that, the method they asked for. All right? So this one, like I said before, I like elimination better, just because I just like how it makes that that first answer easy to get. I think it'd be really easy to cancel out y's, right? By multiplying the second equation by what? 2. And I think we're going to see something interesting happen here. When I multiply that by 2, I get negative 8x plus 2y is equal to 4. And on the top, I haven't changed anything on the top equation. It is exactly the same as what we started. And then I add those together. What happens to the x's? They cancel out. What happens to the y's? They cancel out. Negative 4 plus positive 4. Well, I do. If there's nothing on the left side, it's 0. If there's nothing on the right side, it's 0. Does 0 equal 0? Yes. This is always true. So this is an infinitely many solutions. Infinitely many solutions is what we have here. Because all the variables canceled out, and it was a true statement at the end. No matter which method you use, if we used elimination or substitution, no matter which method you use, the fact that it's a true statement at the end and the variables are all gone is the infinitely many solutions. Okay? Now, one more thing with this. We've got to write our infinitely many solutions in terms of one of the letters, and we normally write it in terms of x. So we need to get what y would look like depending on what x is. And the way that you do that is get one of the equations to have y equals. So I'm going to take negative 4x plus y equal to 2 and just get y by itself. That's all you got to do. It sounds fancy, but it's really not anything. That'd be 4x plus 2. And they're infinitely many solutions. Those solutions look like this. If I pick an x value, I can get the y value that goes with it. If I pick x is positive 3, then y is going to be 14. If I pick x is negative 4, that's going to be negative 14 for y. So we're writing the solutions in terms of x is what that's called. But it's infinitely many solutions. And then this is the ordered pair in terms of x. Okay? And in terms of x is how we would normally write them in this course. All right? So look at this one. Example F. 3x minus 2y is equal to 4. Negative 6x plus 4y is equal to 7. Okay? What do you mean? What do you mean by make both of them the same? I don't disagree with you. I just need to know. How can I, what method are you trying to use? You got to pick either substitution or elimination. Elimination is a good way. So what do I need to turn them into? Times the top by 2, we'll change it into 6x minus 4y. Okay, that's what I'm looking for, and that's what I need you to say. And then negative 6x plus 4y is equal to 7. And on this one, when you add them together, x is cancel, y is cancel, that's 0. 8 plus 7 is 15. Does 0 ever equal 15? No, that's false. Because that's false, that means it's no solution. And that's our favorite occurrence because there's not much work to do for the kid. But it's maybe the least likely occurrence in systems of equations. All right, now, all of that work to tell you that's probably not the best way and the way you're going to solve most of your systems of equations. Those methods are going to be helpful next week when we do nonlinear systems of equations because the nonlinear ones, we don't have a calculator activity that's going to help us. With these, we do have a calculator activity that's going to help us, and it's called a matrix. Okay? So, matrix row operations. We're going to use this thing called an augmented matrix and then reduced row echelon form. You just need to remember the abbreviation RREF. You remember RREF, you'll be okay. Matrix row operations is what we're going to kind of pseudo go through here. I'm going to show you how your calculator will do these row operations for you and get you the answers to a system of equation through a matrix. Okay, so using a matrix for a system, let's take 3x minus 4y equals 1 and 5x plus 2y is equal to 19. Okay. The augmented matrix for that, and this is what we need to know for our calculator, is to know what the augmented matrix is. The augmented matrix is the coefficients of the x and y and then what it's equal to in the first row. And a matrix is just an organization of numbers. And we're going to use brackets to organize those numbers. You will have rows and columns. Each equation is a row. Each variable is a column. So the x's have a column, the y's have a column, and then these that don't have variables will have a column. Okay? And they need to be in order. Each equation needs to be in the same order. Okay, so we have x's, y's, and numbers. So we have two equations, and that'll be 2 rows, and we have 3 columns. So this is a 2 by 3 matrix. So we need to know that 2 rows by 3 columns. So we copy over the numbers for the first row, 3, -4, 1. The second equation makes the second row 5, 2, 19. 2 rows, 1 row for each equation, 1 column for each type of thing in each row. Okay? Now, what we're going to do is we're going to take this 2 by 3 augmented matrix and put it into our calculator. So on your graphing calculator, so I'm here at just the regular calculator screen, nothing fancy going on yet. All right? You need to find the matrix menu. So the matrix menu is right here under second and then the X inverse button. So see the one that's lit up in red? Second and that button will get you to this matrix menu. You may not have anything listed there. I've got some stuff where I've used this before. Okay? We need to go over to the edit portion of this menu because we got to put our matrix in there. So we're going to go press to the edit and then pick where you want to put it. I'm going to put it in matrix A, and I suggest you do the same thing. And then the first thing that you're going to put in is what size is your matrix. Ours is 2 rows by 3 columns. So we put 2 by 3. 2 rows by 3 columns. And we're going to enter in the rows and columns of the matrix we just wrote, that augmented matrix. So 3, and just hit enter. -4, hit enter. 1, hit enter. If there's a number already there, you don't have to delete it. You just type in the one you want over the top of it, and it'll erase it. Okay. Second row should be a 5. 5, enter. 2, enter. 19, enter. Everybody catch on to that. I'm going to go through those steps one more time. So I turn my calculator on. I hit second matrix. Go over to edit. Select a matrix to put yours into. This one is 2 rows by 3 columns. And then I type in those rows. 3, enter. -4, enter. 1, enter. 5, enter. 2, enter. 19, enter. Once I've put those in there, I'm ready to do something with that. So I'm going to hit second and mode to go back to the regular calculator screen to get out of that menu. All right. The next thing I want to do is do some math with that matrix. So I'm going to hit second matrix again. Notice the middle option is math. We're doing math with a matrix, so this is where you do that. So you press the right arrow key to get to the math menu, and we're going to scroll until we see the letters RREF. RREF. So scroll down, kind of close to the bottom. I'm going to scroll up so you can see a little bit better. Mine is on choice B there. Yours should be somewhere around that. It's down toward the bottom. RREF, that's the one you want. You do not want REF, you want RREF. Reduced row echelon form. That's what that stands for. Okay? Hit enter. Reduced row echelon form. Now it says, okay, you want to do RREF? To what? Now we pick which matrix we put that into. So we hit second matrix, choice number 1. For matrix A, because that's where I put mine. If you put yours in matrix B, you would pick matrix B. So wherever you put it, okay? Well, we haven't hit enter yet, so there shouldn't be an error. So now I'm going to close that parenthesis and hit enter, and I should get a matrix back. That matrix I get back, 1, 0, 3, 0, 1, 2, tells me what was in the first column? X's. Look here. There's a 1 in the first column. This first row says X, no Y's, is equal to 3. Second row says no X's, 1 Y is equal to 2. So it tells me that X is equal to 3, Y is equal to 2. All right, so let's go through that one more time. So we're hitting second matrix. You go to edit to put in your matrix. 2 by 3. Make sure you put in numbers in all of those spots. So we got 3, -4, 1, 5, 2, 19. Okay? You have to hit second mode to get out of there before you go to the RREF. If you don't, it will cause errors. Okay. So we're back to the regular calculator screen. We hit second matrix, go to math, and RREF. And tell it which matrix, second matrix, which one did you put it in? I put it in A, hit enter, and it tells you that X and Y are 3 and 2. Did you get it to work that time?
No, I'll watch it over and over.
Let's see. Let's get you going because we're going to do a bunch more. You're not putting anything in. That's why you're getting an error. When you get that menu, you hit second matrix and then tell it which one you want to use. You want to use matrix A.
That's what.
That's what you get.
Oh.
You got to tell it which matrix to use.
Okay.
All right. That tells us that x is equal to 3 and y is equal to 2, and we get an ordered pair, 3, 2. And that's the solution to that system. Is this faster than the other? Probably not. It takes a while to type those in. But mathematically, it sure is a lot easier, ain't it? You know, it does it for you. Okay, so let's look at another one. Example H. Let's say we had x plus y is equal to 2, and then 2x plus 2y is equal to 5.
I gotta change that to H3. Change that.
What now?
Okay, where it says names, math, and edit. I've got 1, A, 2 by 3. I gotta change that.
You can edit matrix A again if you want. Yeah, you can use it again. It's not used up.
Okay.
So I would go to second matrix, go over to edit, number 1, and I've got a 2 by 3 again, and my matrix is going to be 1, 1, 2, and then 2, 2, 5. Second, quit. So I'm just putting in that matrix into a 2 by 3. Okay, and then I want to do RREF. So second matrix, math. Go to RREF, and then tell it what matrix I want to put that in, or which one I want to do that to, which I put mine back in A again. And there I get this weird matrix. I get 1, 1, 0, 0, 0, 1, which kind of, when I was relating here, we had x is equal to 3. This says x plus y is equal to 0. And this says 0 plus 0 is equal to 1. Does 0 plus 0 ever equal 1? No. So this is an example of one that has false and no solution, because that last line is false. This would be a no solution. Now let's get into where it really comes in handy to use a augmented matrix to solve a system, and that's with a 3-variable system. So we have x minus y plus 5z is equal to -6. 3x plus 3y minus z is equal to 10. And then the last one is x plus 3y plus 2z is equal to 5. So a 3-variable system of equations. These can be done by hand. My Algebra 2 students at my high school loved when we did these by hand before I showed them how to do it with the calculator. They really loved me after I showed them how to do it with the calculator, after I made them do them for a couple of days by hand. But they can be done by hand, but it's a long process, and it takes, quite a few steps. And if you make a mistake on any one step, you're messed up for the rest of the time. So let's look at the augmented matrix for this one. What size will the augmented matrix for this one be? 3 equations means 3 rows. We got a column for x's, a column for y's, a column for z's, and a column for numbers. So that is a 4-column set. So it's a 3 by 4 is what we're going to deal with here. So it should be 1, -1, 5, -6, 3, 3, -1, 10, 1, 3, 2, 5. So that's the augmented matrix we're going to put into our calculator and use RREF on. So I'm going to calculator, second matrix, go over to edit, do a matrix. I'll pick A because I'm boring like that. It's 3 by 4. And I'm putting that matrix into my calculator. 1, -1, 5, -6, 3, 3, -1, 10, 1, 3, 2, and 5. Before you get off of that screen, go ahead and make sure you got everything in there the right way, the equation is set up, and everything is got the right sign on it.
Is there a way to make my screen smaller? Yeah, I can't see my whole lot.
Not a way to make it smaller that I'm aware of. Just as you go across, check your spots. I'm not aware of a way to make it smaller.
I need my color closer this way.
I don't know of a way to do that. All right, so once you make sure you've got all that typed in there correctly, second quit, and then you're going second matrix, math, RREF. Again, same. Once you get the matrix in there, all the steps are the same. So I'm in matrix A. That's where I put mine. And there I have the matrix.
Mine will show all the stuff. We've got the A, but it won't show the rest of it.
What do you mean it won't show the rest? Have you done RREF yet?
Yeah, and I've got all
No, you haven't
the
done
numbers
RREF.
right
You haven't
here.
hit RREF yet. Got second matrix, math, go to math, scroll to RREF, enter, then tell it matrix A. Do that time?
I want to leave my numbers. I mean, I can't see them.
You haven't hit enter yet. You get something done.
I'll be doing it. I'll go back.
Three, -1. 1, 3, 2. All right.
Like sheep.
So X is 1, Y is 2, Z is -1. That's an ordered triple in alphabetical order. X, Y, Z. That's how the answers are written, as ordered triples. It's always, if they use a different letter, if they use A, B, and C, it's always alphabetical order. X and Y is always alphabetical order. A's and B's, S's, T's, W's, that sort of thing. It's always that way. All right. All right. Let's look at this system. What are we on? J. And say we had X plus 2Y plus Z equals 4. 3X minus Y minus 4Z is equal to -9. And then the third one is 0X plus 0Y plus 0Z is equal to 0. I had it doing good with the colors. Let's mess it up. That's better. All right, that's better. All right. Augmented matrix is going to look like this. 1, 2, 1, 4. 3, -1, -4, -9, and the last row is all zeros. Okay. Because that last row is all zeros, this one is automatically an infinitely many solutions. Okay? Automatically infinitely many solutions. Anytime you run a system of equations and the bottom row is all zeros, completely zeros, it's an infinitely many solutions. Okay? If we put this into our calculator and told it to do RREF, it would still come back with the bottom row being all zeros. It may change some of these numbers up here, but the bottom row, if it's all zeros, it's infinitely many solutions. If it's 3 zeros and something else here, that's a no solution. All zeros is infinitely many. Okay? All zeros is infinitely many. Okay? Now, let's go ahead and put it into a calculator and see if it will simplify it just a little bit for us. Because it will sum. Maybe not much, but it will sum. So I'm going to hit second matrix. Go over to edit. And I'm just going to use A again because it's already a 3x4. And I'm putting that in 1, 2, 1, 4, 3, -1, -4, -9, and then 0, 0, 0, 0. Make sure I got everything. 1, 2, 1, 4, 3, -1, -4, -9. Got all of those in. Out of that, I'm going to tell it to do RREF on that again. And it did simplify it quite, some. It got some ones in the right places. That's what we want to happen. So, but the bottom row still is all zeros. So we know it's infinitely many solutions. The reason we wanted to simplify that is so it's easier for us to write our solutions in terms of a variable. Okay? So if we wrote these in terms of Z, so I'm going to copy this to my notes here so that I can work with it. So this tells me that X minus Z is equal to -2. The second equation tells me that Y plus Z is equal to 3. I can write X in terms of Z by just getting X by itself on that equation, that first equation. If I add Z to both sides, that would say X is equal to Z minus number 2. This one, if I got Y by itself by subtracting Z, that would say Y is equal to -Z plus 3. Then my ordered triple would be Z minus 2, -Z plus 3, and then Z is what we're in terms of, so that's what, it'll just be Z. So this is infinitely many solutions. And the answers there in terms of Z were the easiest to get to because of the way the equations worked out. They had Z's in them. It's the easiest. If we had to write that in terms of X, that'd be very difficult because the second equation doesn't even have any X's in it. So that's why I avoided X's there. Okay. Big thing is infinitely many solutions. All zeros on the bottom line. That's what it's got to have. Okay. All right. Systems of equations. One solution, no solutions, infinitely many solutions. Be able to get those 3 cases. That's what's going to happen. All right. Let's move on to the next section, which is working with matrices or the matrix stuff a little bit more. And pretty much The rest of the night is matrix stuff. Okay, so good bit of calculator things, but still not. Some of it, I'll show you how to do some of it by hand, and then some of it with, all of it I'll show you how to do with the calculator, but I'm going to show you how to do some of it by hand, just because it's quicker sometimes to do it by hand. Okay, so section 5.3 is where we're headed next. Determinants of a matrix. Okay, determinants of a matrix. Determinants. Big question that always comes up when we talk about determinants is, what is a determinant? It's a property of a matrix. That's what it is. It's a number value that tells us something about that matrix. And one of the things it tells you is that matrix invertible or not? Not that that's super important to you unless you're an engineer, okay, or you're doing a lot of systems of equations. So determinant just is a property of a matrix, and so write that down somewhere. Determinant is a property of a matrix. Determinants can only be found for square matrices. That's just the plural of matrix. Square means it has the same number of rows as columns, so 2 by 2, 3 by 3, n by n. Same number of rows, same number of columns. Got to be those, okay? Now, finding the determinant of that, your calculator can do that. I'm going to show you how to do that with a 2 by 2 by hand, because I think it's easier to do by hand than it is to get the calculator to do it, but we'll show with the calculator as well. So, and then when we get to anything larger than a 2 by 2, I think you're better off just doing it with the calculator. So I'm going to show you both ways with 2 by 2s, and then we'll do calculator on everything else bigger than that, because it gets into quite a few operations on anything bigger than a 2 by 2. So on a 2 by 2 matrix, and I'll show you this because it's a quick calculation. A 2 by 2 matrix it'll have pieces in it. They're called elements. The elements are the numbers that are inside there. I'm using letters here, A, B, C, and D. The determinant, there's a couple of different ways they do the notation for this. One of the ways is the word DET, and then they put the matrix in there, A, B, C, D. That is notation for find the determinant of that matrix. That's one way to do the notation. The other notation is absolute value looking marks. So if they put a matrix inside of what looks like big absolute value marks, that's the determinant. They're saying find the determinant of that. The determinant of a 2 by 2 just takes cross multiplying. A times D minus B times C. For a 2 by 2, that's easier to do than type it in your calculator. It takes less time than type it in your calculator to just do that math. Okay? We're going to do it both ways. Show you how the calculator can do it and how you can do it by hand. So let's take the determinant of 2, -3, 5, 7. That is a 2 by 2 matrix. We can see it has 2 rows and 2 columns. And to do that by hand, you just take 2 times 7 minus -3 times 5. Should be 14 plus 15, which is 29. Quick and easy to do. Your calculator can also do that. You go to your calculator, go to matrix menu, go over to edit. I'm going to put a 2 by 2 in. And it's 2, -3, 5, and 7. And then I'm going to do some math with that. Again, I'm going to get out of the matrix menu, go back to the home calculator screen. I'm going to hit second matrix, go over to math, and the first option, I'll have to scroll anywhere, it's DET, that's determinant. Determinant, and then I pick the matrix I want to find the determinant of. Number 1, and it gets me 29 as well. By the time I type it all in, I could have just done the math. That's why I do 2x2s by hand instead of with the calculator. But understand, you can do it with the calculator. I don't care. Either way, okay? No one will ever know. All right, let's look at another 2x2. Determinant of 10 2/3. So you can have fractions inside of a matrix. 9 and -6. All right. If I do that by hand, that'd be -60 minus 6, be -66. Just cross multiplying and doing it in my head there. If I do that with the calculator, second matrix, edit, got a 2x2 there, 10, and to put in 2/3, you just type 2 divided by 3, and it'll convert it into a decimal, but it's showing it rounded there, but it's not rounding it at all. It's stored all of those digits there. They're not rounded at all. And then 9 and -6. Second quit. I've already used DET of A. If I just press the up arrow and highlight that and hit enter, it's using a different matrix now, obviously, because I got a different number. It's -66, just like I found when I did it by hand. Yes. Yes, absolutely. Anytime you've already used that and you put it in the same spot, you can just go copy paste. Kind of is exactly what it is. It's a copy paste feature. Out of that, you can use that. That speeds you up a little bit. Not a whole lot, but some. Okay. Now a 3x3. Remember, it's got to be a square matrix to be able to find the determinant of it. Otherwise, it's undefined. If it's not a square matrix and they say to do the determinant, you just write undefined. It's not possible to do that. So here's a 3x3. 6, 2, 4, 8, 9, 3, 1, 2, 0. If you want me to show you how to do this by hand, I will.
No.
But it's a lot of operations. A 2x2 took 1, 2, 3 operations. A 3x3 takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 operations to do. And it's once it gets past a 2x2, it really grows fast how many operations you have to do. Imagine a 10x10. If a 3x3 takes 15 or 16 operations, a 10x10 is going to take, probably about 100 operations, depending on the numbers in it. But just one 10x10 by hand? You willing to miss that one? No calculator. It'll take me 2 hours. It'll take you 2 hours to go. All right, so let's put that 3x3 in there. So second matrix, edit. I'm gonna go 3x3 on the first one. Let's put that in there. 6, 2, 4. Whoops. 6, 2. Enter. 4. Enter. 8, 9, 3, 1, 2, and 0. All right, and then I put it in A again, so I'm just going to do that copy paste thing. And I get a determinant of -2. Just finding the determinant is one of the things that you do.
Okay, if I get that in there, then what, how'd you get the equal? I missed it. I got all my numbers in.
So second mode to get back to the regular calculator screen.
Second mode.
Yeah, to get out of the matrix menu, and then second matrix over to math
So back in.
and get the determinant, and then tell it which one you want to do the determinant of, which is number 1. And that's how. Yeah, it'll take you a minute, but it's all just learning keystrokes out of that. Now, I am required to mention to you that there's a thing called Kramer's rule that uses determinants to solve a system of equations. That is a long way to get answers when you could just use RREF. Okay? But you know there is a thing called Kramer's rule. It's not Cosmo Kramer from Seinfeld, if anybody watches that show still. I still watch the reruns of that. It's still funny. And so, it's Kramer with a C. So Kramer's rule exists. You don't have to do it. You can find the answers another way. Okay? So just anyway, you know it exists. Okay, so there's that section. Let's go to yet another section. Section 5.7. Yeah. We have 5.7 and 5.8 to do, and then we're gone.
Here we go.
We're done. Yeah. I ain't gonna get to watch them no way. An hour drive home. They'll be done by the time I get home. I'm driving. I can't watch it while I'm going down the road. That's what? Let's just move on. Properties and matrices. I don't want to get into that. All right, so properties and matrices. So these are just going to be things that we can do with matrices, operations with them, different things that can happen. One of the things that we're going to do is called row operations. And when we were doing that RREF, row operations are what your calculator was doing to that matrix in order to get it in the form that it was. What you need to be able to do, and there's always, and I mean, when I say always, I mean every year and every semester, Math 110, on the final, there's a row operations question. They give you a matrix, such as this one. So I'm just going to give you this matrix. Doesn't matter what size it is. We're not solving the thing. We're just doing row operations with it. So I'm just going to throw one up here. Oops. That's a -8, 10. Yes, oh, absolutely. But it's pretty easy. Okay, so here's your original matrix to start with. And then they will tell you what row operation to do. They're going to give you instructions as to what row operation to do. They're going to tell you, say, okay, take that matrix and do this. Do 3 times row 2 and change row 2. What does that tell you to do? It says take 3 times row 2 and change row 2. That's what that says to do. So what's row 2? The second row. Multiply that second row by 3 and change that row. That's all you're doing. Okay? So your answer for that would be 3, 21, -27, 12. The other 2 rows, did it say do anything to those? No. So guess what? They stay the same. Exactly right. So we got 3, 2, 6, -5. And then the bottom row is -8, 10, 2, -13. Okay? We only change the row it says to change. Okay? Okay? Then let's pretend that that's our original one now. The blue one is the original one. And let's do a different row operation. So example B would be do this row operation. Row 1 plus row 2 change row 1. Okay, so that's an addition problem with rows. But which row is changing?
Only row 1.
Only row 1. So that means these 2 rows we're going to copy. Okay, so I'm going to copy those first. Bless you. Okay, so 3, 21, negative 27, 12, negative 8, 10, 2, negative 13. Now, row 1 is the one that changed. Like this. Row 1 plus row 2, change row 1. So 3 plus 3, 6. That goes in that first spot. 2 plus 21, 23. 6 plus negative 27, negative 21. 12 plus negative 5. 7. Thank you. We've done that row operation. It really is not any more difficult than that. Let's do one more. Example C. Let's take 1/3 of row 2 and add it to row 3 and change row 3. 1/3 of row 2, add that to row 3, and change row 3. So, what about row 1 and 2? They stay the same. So 6, 23, negative 21, 7, 3, 21, negative 27, 12. Now I'm going to use row 2, but I'm not changing row 2. I'm only changing row 3.
But you gotta do more math.
Got to do some math with it, right? So 1/3 of 3 is 1. 1 plus negative 8 is negative 7. 1/3 of 21. 7 plus 10. 17. 1/3 of negative 27. Negative 9 plus 2. Negative 7. 1/3 of 12. 4 plus negative 13. Negative 9. 4 plus negative 13 is negative 9. And we've changed row 3. One other thing that I'll mention here, we won't even do an example of this, but if it said row 1 and then row 2 here and had a double arrow like that, that just means swap them. Swap the rows. That's what that means. And so that arrow there means swap rows. So if you see that, it means swap rows. That's not a very common row operation that they put out there, but that's what it means if you see that double arrow like that. So swap rows. No, linear algebra is what linear algebra is what it's called. It's one of the big parts of electronics and electrical engineering is a big linear algebra type thing. All right, so let's do the next operation with matrices, and that would be adding and subtracting matrices. Adding and subtracting matrices. They must be the same size. So in order to add two things together, it's got to be 2 by 3 plus 2 by 3. It's got to be 4 by 4 plus 4 by 4. It's got to both. Any matrices you're trying to add together have to have the same size, same number of rows, same number of columns. Got to have those. If it doesn't have those, it's undefined. Okay? If it doesn't have the same size, it's undefined. Okay? So couple of quick examples of that. Let's take this matrix, 5, -6, 8, 9. What size is that? 2 by 2. So to add something to that, I got to have something that's what size? 2 by 2. -4, 6, 8, -3. Now, when I add these two together, tell me how you think it works. Yeah, corresponding parts. Location. Mr. McGrady's likes a good picture. Location, location, location. So 5 plus -4. So top left, goes together. Matching up places. 5 plus -4 would be 1. -6 plus +6, 0. 8 plus 8, 9 plus -3, 6. Now, that's doing it by hand. You can do that with the calculator. If you go to your calculator and put in the matrices, 2 by 2, and 5, -6, 8, 9, quit, go to second matrix, go over there to edit again, and pick a different matrix this time. I'm going to use matrix B, 2 by 2, and then -4, 6, 8, -3. Second, quit. Now I got to tell it to add those together. So I'm going to go to second matrix, and I don't have to do any special math operation here. It's just addition. So I'm taking matrix A plus second matrix, and then matrix B, and hit enter. Oops. Enter. 1, 0, 16, 6, just like I did by hand. I usually don't type them in the calculator to do addition or subtraction, unless it's like fractions or something like that. Or a really, really large one that I could easily get off on. Got to be the same size, okay? Let's look at another one. Again, addition, subtraction. So 8, -10, 6, 5, -7, 18, minus 6, -4, 1, 8, 5, 9. What size are these? Nope. 3 rows by 2 columns. Rows by columns. Rows and then columns. So 3 by 2s. And both of them are the same size, so that means we can do this subtraction. It's going to be a 3 by 2 when we get done. So we just do that corresponding parts. 8 minus what? 6, which is 2. 10 minus -4. -6. 6 minus 1. 5. 5 minus 8. -3. -7 minus 5. -12. 18 minus 9. 9. And again, you can type those in your calculator and tell it to do that subtraction the same way I just showed you how to do the previous example. And it will get you that matrix back. Matrix addition and subtraction is straight up, got to be the same size, corresponding parts. Or they're called elements, corresponding elements. Location, location, location. Right? If they're not the same size, then it's undefined. Undefined. Not the same size is the word undefined.
But it can have fractions.
It can have fractions, it can have decimals, it can have all kinds of other numbers in it. But if it's not the same size and it's addition or subtraction, it's undefined. Okay? All right, next type of operation. Scalar multiplication. Multiplication. Scalar multiplication has no rules as far as it doesn't have to be a certain size to be able to do scalar multiplication, because scalar multiplication, I want you to think it's like distributive property. Spells distributive. So when you see this, you're thinking distributive property is what you should be thinking. All right, so an example, you have a matrix, 6, -8, 10, 2/3, 4, -13. And the scalar will be written out here on the front. Like maybe the scalar is the number 3. That scalar distributes to every element of multiplication. This one happens to be a 2x3 matrix. Doesn't matter what size it is. Scalar multiplication is just multiply everybody on the inside by the number that's on the outside. 3 times 6, 18, -24, 30, 2, 12, -39. And we've done the scalar multiplication. Again, you could do that with your calculator. If you went to the matrix menu, edit, 2x3, and I put in that matrix, 6, -8, 10, 2/3, 4, -13. I put that into matrix A. I want it to say 3 times matrix A. And there I get that same scalar multiplier. So scalar multiplication, no rules as far as being able to do that with certain sizes. It's a plain number on the outside times everybody on the inside. That's all scalar multiplication is. Really one of the easiest things in matrix algebra. All right. Last operation with matrices that we'll talk about is multiplying matrices. So this is not scalar multiplication. This is multiplying a matrix by a matrix. One key thing to remember is this is not commutative. In math, most of the time multiplication is commutative, meaning 2 times 3 is 6, just like 3 times 2 is 6. You can swap the order and it doesn't matter. Matrix multiplication, you cannot swap the order. So when you type it into your calculator to do this, it's got to be in the order that it's written. If it's not, it's going to give you either no answer or a completely different answer. Okay? Now, one of the reason that is not commutative is the left matrix columns must match the right matrix rows. Example being if you had a 2x3 times a 3x4. Those numbers in the middle match up. So that means that this is a valid multiplication of matrices, and it would end up with a 2x4 at the end. So numbers in the middle, when you look at the dimensions have to match up in the middle. The outside edges are the size of your answer. I'll show you this with 2 matrices here. Do some multiplication. I do not ask you to do multiplying matrices by hand, ever. Okay, you will not have to do that for me. If you are going on to linear algebra, math 310, or some sort of engineering type program, you would probably have to be able to do this by hand. I'll let that teacher worry about that. I'm not asking you to do it, calculator. Okay, so, if you want to know how to do it by hand, I'm sure I've got a video somewhere on my YouTube channel you can search through and find that's me doing this by hand for my algebra students at school. So, but you guys, I'm not. It's not going to help you to be able to do this by hand. It's just going to frustrate you because it's just like the determinants for a 3x3, there's a ton of operations and just a ton of places to make mistakes. So let's let the technology work for us, okay? So example, is this G? Is that the right letter?
Yep.
All right. 1, -3, 7, 2. And matrix B, we're going to call it 1, 0, -2. I mean, -1, +2. 3, 1, 4, -1. Okay? I just went ahead and named them A and B so that we are all putting them into the same spot or calculator. Okay? What size is matrix A? 2 by 2. What size is matrix B? 2 by 4. Okay? So when we multiply A times B, we're taking a 2 by 2 times a 2 by 4. The numbers in the middle match up. So that means that this is a defined operation and that we will get a 2 by 4 as a result. Okay? 2 by 2 in the middle. The 2's match up. So that means we will get an answer. That answer will have the size that's 2 by 4. That comes from the outside. So to do that, let's take our calculator and put in those two matrices. So second matrix, go over to edit. So I'm doing a 2 by 2 for matrix A, 1, -3, 7, and 2. Second mode, second matrix. Go to matrix B under the edit menu. It is a 2 by 4. 1, 0, -1, 2, 3, 1, 4, and -1 is the last piece. Okay? So I've put those two matrices in my calculator to try to multiply them. Okay? All I've got to do is tell my calculator to multiply matrix A times matrix B. So I hit second matrix, pick up matrix A's name, times second matrix, matrix B's name. Enter. I get a 2 by 4 back. 8 or -8, -3, -13, 5. -8, -3, -13, 5. Second row, 13, 2, 1, 12. 13, 2, 1, 12. That, A times B. That's what that equals. Now, if I ask you to do B times A, that would be a 2 by 4 times a 2 by 2. Those don't match up. This is undefined. If you didn't think to check that before you put them into your calculator, and you just went ahead and put them into the calculator, and I tried to get my calculator to do that, second matrix B times second matrix A, it's going to give you this error, a dimension mismatch error. That just means it's undefined. Okay? So you can't get, if you put them in correctly, you're not going to get the wrong answers here. You're going to get an error here if you put it in backwards and it doesn't work. But be careful, because if you were multiplying a 3 by 3 times a 3 by 3, you could get an answer both times. They would be different answers. Make sure that you're doing it in the right order. Okay? Make sure you're doing things in the right order, because matrix multiplication is not commutative, meaning it won't always be undefined to do it backwards. You can get answers by doing it backwards, depending on the size of the matrix that you're dealing with. But you've got to be careful about order, because order matters in matrix multiplication. There is no such thing as matrix division. Okay? Doesn't exist, which is nice. That means we're done with operations. Okay. All right, same section. Next thing in this section is equal matrices. I've always called these matrix equations, but this particular book has another name another thing that it calls matrix equations. So they call these equal matrices. Same thing. So if you Google matrix equations, you're likely to find what we're about to talk about and what we're going to talk about in a little bit. So equal matrices is what this textbook calls these. Okay, so equal matrices mean that two or more matrices are what? Equal, meaning that they have the same things in the elements. So like element in the top left corner is equal to the element in the top left corner of the other matrix. So what it is it's like an equation. You've got maybe 2, 1, P, and Q is equal to X, Y, -1, and 0. Something really just abstract and weird. There's no math involved in working this. It's just equal matrices. You have a 2 by 2 matrix over here. You have a 2 by 2 matrix over here. If they're equal to each other, they got to be the same size. And pieces have to match. So what does X equal? 2. What does Y equal? What does P equal? Q? 0. All matching spots, okay? So that's what we're finding here. It's X equals 2, Y equals 1, P equals -1, Q equals 0. That's what we're finding, those variables that are buried inside of these. This is not a system of equations. They may use X and Y a lot, but it's not a system. It's a matrix equation or an equal matrix. Okay. Where it looks a little bit more like what I like here would be something like this. 7x3 -5 10 y plus, and then let's get another matrix. 8 -6 10 5 16 7. That is equal to this matrix. 15 10 13 0 26 14. Little squiggle there is a 13. Better. Okay. So here is a little bit more complicated look at this, but it's still equivalent matrices. Okay. So you've got 2 matrices over here that are added together, and they should equal this one over here. If we look at corresponding elements, 7 plus 8 is equal to 15. Well, that matches up. X plus -6 is equal to 10 because they're all the middle of the top row, right? So that sets us up an equation to solve. That if we can find out what X plus -6 is equal to 10, the reason I'm using that is because they're all right there in the middle row. The middle of the first row. So if I solve that equation, X would have to be 16. Because 16 plus -6 would be 10. That's why X has to be 16. You see where we're going with that? Okay. So what would be the equation so that we could find Y? Y is right here. What goes with it? That 7 right there. And it should equal to 14, right? So Y plus 7 should be equal to 14. And then subtract 7. Y's got to be 7. Just setting up the equations, just using the matching elements. That's all this. It's really not much more complicated than that. Let's do one that's slightly more complicated, but still not too hard. Maybe they got a 2 and then 3x -1 5 5 minus 1, 8, 10, and 2. And that's going to be equal. It needs to be a 2 by 2 that it's equal to. 5. And let's say that that's, let's make that a 4 there. And then 12. Okay. So there's us one made up off the here. So that 2 is hanging out in front. That 2 is called a what? Scalar, right? So it means it does what to everything on the inside of that? It's multiplying, okay? So 2 times 3 is 6. 6 minus 1, 5. So we see that that's how that's working. What would be the equation we could set up for x? 2x minus 8 equals 4.
And the scalar's only done with the equation of the side.
With the matrix,
it's
right. Only the one that's right beside. Yes, ma'am, that's correct.
Okay.
All right, and then we can solve that equation pretty easy. Add 8. 2x is equal to 12. So x has got to be 6. There are no other variables in there. I'm done. That's the only one that there was for this problem. The small one, 2 by 2s are not real big. But the idea here is that scalar multiplier has got to be taken care of. Yeah, as you're going. And if you wanted to go ahead and multiply everything in here by 2 and then rewrite the problem, and then write the problem down, that works just as well, maybe better for some of us. Or if you could just think about it, like we did there, that works too. Okay, so scalar multipliers thrown in there can cause things to happen. All right, now let's look at the last section for the night. Not very many examples in it. It's a pretty short section. But it's matrices stuff, and it's mainly calculator stuff. Okay, so new section 5.8, and then we'll go back next week. We'll go back and get 5.5 and 5.6 with the nonlinear systems and then systems of inequalities. So a little bit of graphing going on there. So matrix inverses. Okay, I told you that matrix division did not exist. This is the, I won't say equivalent operation, but it's the idea of dividing by a matrix is the same as multiplying by its inverse. So matrix inverses are our way around of not being able to divide using inverses. And what we're dealing with when we're finding the inverses of matrices, it's kind of like, what's the reciprocal of 3?
1/3.
1/3. What's the reciprocal of 4 over 5? 5 over 4. That kind of, the multiplicative inverse and reciprocal, those are the same things. When we're finding matrix inverses, we're talking about multiplicative inverses, or it's kind of like the idea of a reciprocal of a matrix. It's not as simple because it's a matrix and not just a plain number. But that's the idea that we're dealing with here. That's what a matrix inverse is. All right. So we need to define this thing called an identity matrix. All right. An identity matrix, what it does is it acts like a number 1 in regular numbers. All right, so if I multiply by an identity matrix, I get the same matrix back. Just like if you multiply 6 by 1, you get 6 back. You multiply 112 by 1, you get 112. An identity matrix does the same thing. The difference is identity matrices can be different sizes. Okay, and so when we talk about an identity matrix, the size, if I say I2, I'm talking about a 2 by 2.